Hello, I'm Bryce Bedard,
I'm Jeff Evans.
and our senior project is a solar-powered smart home.
Currently, we are finishing up both our degrees in electrical and computer engineering technology.
So, our project was to simulate a smart home powered by solar energy. We designed the home to be energy efficient and as well as include various smart home capabilities, including automated lighting, automated shades, heat, and a security system, as well as user-controlled lighting, shades, and heat. And both of these were combined into a single LabVIEW GUI. Part of the project was also to encourage the widespread use of residential sustainability.
Some of the courses that our project aligned to are digital logic. This is where we learn Boolean logic, to which we use extensively in the project. Alternative energy generation. This is where we learn renewable energy and how to design photovoltaic systems. Instrumentation is where we learn data acquisition, system calibration, and mainly LabVIEW. Embedded real-time systems, where we learn to design and implement real-time operating systems. And feedback control systems, where we learn to design and implement closed-loop control systems.
So some of the house features include a simulated 10 kilowatt solar array designed via PV watt calculations, motion controlled lights. These are done through motion detectors in the house. When one motion detector is set off, the lights in that room will turn on. When a motion detector is set off in another room in the house because you have moved there, the first room's lights will then turn off because it detects you're no longer there. We also have automated blinds, which will can be activated via a wireless remote, as well as an automated gate and garage, which will activate upon arrival home. We also have energy efficient heating, so during the day we have a lower set point for the house than during the evening. That way heating doesn't kick on as much during the day when electricity is more expensive, and it'll kick on more so during the evening times when electricity is cheaper. We also have automated security and fire protocols. When an intruder breaks in, all the shades in the house will then close, essentially trapping the intruder inside. Lights in that room will also flash. We also have, in case of a fire, all the shades will then rise. We also have SMS notifications in case of intruder or fire. So the user will get a text message notifying them that a fire or an intruder has broken into their home. This can also be set up to alert the authorities in a real life scenario. We then also have energy generation and usage monitoring and manual controls, all incorporated into the LabVIEW GUI system.
For our photovoltaic system, we designed it to optimize during the spring and fall months. The energy that we needed by the photovoltaic system is roughly 60 kilowatt hours. This results in a peak draw current of 674.6 amps, a corrected amp hour load of 788.99 amp hours per day, and then this results in a design current of 165 amps. How we calculated solar radiation, we used PV watts calculator by NI During the fall semester, we had an average of 4.78 peak sun hours per day, and during the spring semester, we had an average of 4.52 peak sun hours per day. This system results in 14,922 kilowatt hours per year, and that translates to a savings of $1,379 per year. The power needed from the photovoltaic system was calculated out to be 9,698.1 watts. And when you divide this by the wattage per panel, 300 watts, we got roughly 33 panels needed, which is a typical size of a house, photovoltaic system. Then a battery capacity, which was planned for 1 day without sun, was calculated to be 2,840.5 amp hours.
So because our program or our project is all simulated, we had to use various softwares to complete the project. The first software being Realgames Home I software, where we used just the one sandbox program, which incorporated all of the various programmable devices. We also then used 2 Realgames Connect.io programs. The first one running the automation of the house, as well as including security and fire protocols. And the second one being only security and fire protocols, which would then be used if the user switched over to manual mode. And then finally, we use National Instruments LabVIEW 2018 edition, where we use 35 different VIs to complete the GUI.
So the Home I software is a house simulation with 170 different programmable devices, and this allows you to interact with the environment within the simulation. Devices include dimmable lights, door detects, motion sensors, shades, heaters, a security system, and a smoke alarms. You also have the ability to change location, date and time, temperature, wind speed, cloudiness, and humidity. There's also a remote that is programmable within the simulation. So as you notice, when you approach the gate, there's an infrared sensor, and once that is triggered on the rising edge, the gate will open. And once you pass through, there's a second infrared sensor, and on the falling edge, once the car is completely through, it will start to close the gate. And as you can notice, when you approach the gate, the garage door also opens. And when you go through, there is a third infrared sensor that detects on the falling edge, like when you're completely in the garage, it will close the garage. We will move into the house in the living room. As you can see, the lights will turn on automatically. And then we will show the shades using the programmable remote. So button 5 will raise all the shades in the house, and button 6 will close all the shades. We will also briefly show the smoke alarm. So we'll drop smoke, and as you can see, in response, the house will automatically raise the shades to allow more air ventilation. To program the simulation, we use Connect.io. This is a graphical programming language used to program the simulation and allow external technology to interact. Some of the smart home automation processes include PIR lighting. This increases efficiency, and we also have it set to flash, lights flash in the room where a break-in occurs. There are automatic shades that will open and close at set times, provided that is enabled. They will open with smoke as demonstrated before, and in an event in a break-in, if the shades are open, they will close. We also automated the gate and garage to open and close upon arrival. Heating, which has a user set point, and during times when no one is in the house, it will increase that differential, which will make the heaters kick on less and save energy when you're not at home. The smoke and security system enacts safety protocols. Here's a simple cutout of the program. Green indicators are inputs, all the red indicators are outputs, and all the gray things are functional blocks for logic programming, such as JK flip-flops, AND gates, OR gates, set resets, like latch functions, and triggers, rising and falling edge.
So next up we have the LabVIEW program. This consisted of 35 different VIs. Our first VI was our main VI, which would then load in all the other VIs into it so that the user could interact with all of them individually. This also contained a switch to switch between the automation and manual modes that the house allows. And the next VI was a global VI, which the user actually can't see, but holds 96 different global variables, which are placed throughout the other VIs so that all the VIs can transfer data from one to the other. We then had 15 control VIs, which would act as indicators during automation mode, and will actually act as controls during the manual mode, so the user can interact with the house. We then have 18 different energy VIs. 15 are coinciding with the 15 control VIs mentioned earlier. So it shows the energy of each room excluding heat. So when loads are turned on, it will show both the power and energy, overall power and energy for that room. Then we have a single VI to separate the heat from the rest of the loads of the house because of the power for the heating is just tenfold higher than the rest of the loads of the house that are being demonstrated. Then we have another VI to show the energy being generated by the simulated solar array. And then finally we have a VI which will sum up all the individual room energies being consumed and compare that to the overall energy being generated for the house. Next up, we'll show the LabVIEW program. So, as you can see, each room has its own controls. And then we can also go over to the energy, and each room has both power and energy consumption. So, challenges and how we solve them as far as the project goes. Our main challenge was getting Connect.io and LabVIEW to work cohesively together. The main issue between the two was that Connect.io only allowed you to write to outputs and read inputs, and not vice versa. So as far as LabVIEW goes, during the controls, that was fine because we could write to, if there's a light, we can turn it on. But during automation mode, we couldn't read whether the light was on, so we had to replicate the logic used in Connect.io to see whether a light switch was pressed, a PIR was active, or if a dimmer was clicked on. And doing that, we were able to indicate whether a light was on in automation mode, and we had to do the same with shading and heating as well. The next issue we had was the time delays of the two programs. Connect.io was originally set at 15 milliseconds. We then upped it to 100 milliseconds to save on CPU power, as well as working better with LabVIEW. LabVIEW was set at 300 milliseconds for the controls, because anything less would risk the issue of reading a singular input as two or more. The next issue was severe lag due to the Connect.io program. Connect.io is very CPU intensive. Part of the reason why we upped the cycle delay was to save on CPU resources, and then even still it was running at taking up about 50 to 60% of CPU resources. So to solve this, we actually went back in and cleaned up the Connect.io program and reduced redundancies, which actually ended up cutting the CPU usage by half, and made the program run much more smoother. The next issue that we had was trying to use data collection via the fast forward feature of Home I/O. Home I/O has a fast forward feature that can go from normal speed up to 5,000 times normal speed, so we could simulate an entire day in 17 seconds. The issue was with LabVIEW not being able to keep up with Home I/O, so data would actually come in much lower than what it should have been. To solve this issue, we took data and came up with various spans to use depending on how fast the fast forward function was operating at. And although it's not perfect, it's very close and very accurate. And then finally, our last main issue was that we only had we began with only one license of Home I/O, which was put on Jeff's laptop. That meant anytime I was working on the project and got to a point where I needed to test something before moving on to avoid replicating the same issue, it would usually have to wait till at the very least the next day due to our schedules not being in sync. About halfway through the project, I ended up purchasing a second Home I/O license, and that sped up the project completion tenfold.
So for future improvements, tracking any intruders, and this would be a simple addition to the project, simply using PIRs to track any movement within the house and keep track of where the person is located. And in return, you could send that data to LabVIEW or your local authorities. Another thing was to improve our spam algorithm that we use. It could definitely use some tweaking over time, because we got through this pretty late. That'd be a very good project. We could also include external physical controls to interact with the simulation. We could add a login screen for different users or family members that live in the house, and then create a database to show data and trends over time. And this would greatly help with energy conservation and learning more about that topic. And lastly, a great idea that we just came up with is to automate weather based on real world weather conditions. And this would be done by using the Arduino IoT weather station. So wrapping this all up, our goal was to simulate a smart home and power that using solar power. Because this was a simulation, we definitely had a lot of things to work through, but we achieved our goal, and the photovoltaic system worked well during non-winter months. Another goal of ours was to promote energy efficiency, and this was done through PIR lighting and changing heat temperatures throughout the day, and as many smart home automations as possible, and also security. We implemented real world advantages of security as alerting you when you're not home when something happens, and also any local authorities.
Through this project, we learned how to incorporate multiple softwares to make a single cohesive project. There was plenty of troubleshooting, but through that we used fairly advanced programming methods to, as far as Connect.io and LabVIEW goes, to get them to work up synchronously. And then finally, although we believe that we've done quite a bit with this project, there's always room for improvements, such as the things we mentioned earlier. So our files could actually be used as a shell for students in future projects if they wish to upgrade the project, including some of the things we mentioned earlier, or if they just want to customize it to their own personal preferences as well. In our references, you'll find links to Realgames' websites and information about the Home I/O software. Thank you for watching our senior presentation.